Cool. So new topic, we're going to do level curves, which is the idea of if you were a helicopter looking down on some mountain range, you would be able to sort of see the different altitudes happening. And what we do is we actually can graph what's known as level curves. So if you look at this surface on the right, you can think of that as being a mountain range, and that's sort of got the hot pink. And then there's a plane there and a flat surface that's sort of in yellow or gold. And what I'm doing here is I'm dragging a slider that's dragging that plane down and then back up. And if I stop the plane halfway, these curves that you see on the left, those are what are known as level curves. Okay, yeah. And where the curves get really close to each other, the ones that are closer to each other over here in the corners, that means that the altitude is changing very rapidly at those.
All the points on the red line are equal to n.
Mm-hmm. Yes. So n here is like some number, it looks like here, right now I just stopped it at 0.3. So everybody at that location is at the altitude 0.3. And if I drag the plane a little higher, altitude goes up. You see that the level curves change a little bit more, so it only goes up so high. And there's about the highest I can get it. So when these level curves are not very close together, that means at that point that the altitude isn't changing as rapidly. So this is good for hikers. You know, let's say you like hiking really steep hills because you like getting a good workout. You'd be interested in hiking on some ranges where these level curves are very close to each other because it's going to be steep. On the other hand, you're like me and you don't want to have it too much hills, you'll be hiking where it's not so close together. So that's the idea of level curves. So let's take a look at that concept here. So here's level curves. You see one of these kind of maps called a topographic map. Yeah, so closely spaced contours, that means rapid changes in elevation. Widely spaced contours, slow changes in elevation. Pretty cool, huh? So here's a surface. Let's say it was given by some function z equals f x comma y. The contour map is where you draw all these level curves. So it's showing you the variation of z, the variation of the altitude with respect to x and y, with the spacing of the level curves. But how do you graph one of these? I'm going to show you in detail how you come up with your own graph for level curves, right? If you follow my step-by-step procedure, you'll be swinging it in no time, all right? So they're just showing you this idea of a plane that's level, a level plane here, and they're moving it up and down for different altitudes, and you're getting different curves, okay? So at this height, z equals z1, this circle here is shown right there. On the other hand, when the altitude's a little lower at z equals z naught, it looks like it's also the trace as that plane is cutting through that mountain is all, it looks like it's kind of an ellipse now. You get the next curve, okay? And they're just showing you some more pictures here. This is kind of cool. Now let's do one ourselves. Okay, so here you go. And you'll have these in MyLab Math. And when you're doing handwritten work, I like to see all the steps. So if you have the right answer, but you're not showing me the steps, I won't give you all your credit. So you want full points, follow my procedure. Step one, and I better see this on your paper. You set your function, fxy, equal to a constant. Because that's essentially what's happening when you're trying to find level curves. You're looking at a fixed altitude. So this is a constant. Which constant is it? It doesn't matter at this moment. For now, let it be a constant c, and you'll plug something in a moment. So what is fxy? Well, for this particular problem, it's square root of 64 minus x squared minus y squared, and you're going to set that equal to c. That's step two. Now, after step 2 here, you may want to go a little bit further because that doesn't look like anything familiar, at least not to me. I'm going to rearrange things a little bit. So I'm going to square both sides because I can. Get rid of the radical. And then how about if I move the x squared and y squared over to this side? And how about if I move the c squared over to the other side? Now this equation looks like something. It reminds me of the equation for something you did in pre-calc. And I claim this looks like the equation for circles centered at the origin. And so it's going to turn out all of the level curves for this particular surface are going to be circles centered at the origin. Well, what's their radius? Well, that depends on which constant you're going to feed this equation. So like if you let c equal 0, then the level curve associated with the altitude of 0 is going to be x squared plus y squared equals 64. So if I were starting my graph here, that's going to be a circle of radius 8 centered at the origin. And I can plug in different values of c, okay? So like what about c equals, I don't know, 7. Okay, c equals 7. You're going to have 64 minus 49. And that's going to be what, 15? So you're going to have a circle of radius square root of 15. Oh, that's going to be kind of weird, you know, something like that. So you're just going to get a bunch of concentric circles, essentially, okay? You can kind of see what's going to happen there. Here's your contour map. Let's do something that's a little harder. What about, oh, by the way, this original surface here is the upper hemisphere centered at the origin. See, and they graphed it for you. So it makes sense that when you start slicing through it, that you get circles for level curves. Now, what about something harder, like that thing? Like, what the heck is that? And again, I'm not going to ask you to graph stuff in 3D. You know, although my math lab does have problems where you have to go into GeoGebra and do stuff, and I did not give you those because sometimes they don't load properly, and I don't want to get into situations where you guys have loading issues. So what does that look like? That looks like that hyperbolic paraboloid again. Some people like to think of it as a Pringles. So I like to think of it as a horse's saddle. But you know, what would the level curves for that guy look like? Well, let's see. So follow my procedure if you want all your points. Step 1, set the function equal to a constant. Uh-oh. Woo! So in this case, y squared minus x squared equals a constant. Now, what does that remind you of? Try to use your pre-calc knowledge. I claim that these are hyperbolas. Well, which kind? Up, down, or left, right? Turns out both. It depends on what c is. So let's say we let c equal 4. Have it be a positive number. So then we'd have y squared minus x squared equals 4. And so if I were to graph the hyperbola for y squared minus x squared equals 4, this would be what I call an up-down hyperbola. Yeah. I can't write right now, sorry. So I think the 2 and -2 would be the y-intercept, and it would look, you could figure out how fat it is by doing a little bit more work. I'm not going to do too much work here. So that's the picture of that. Now, what if c equals -4? So what if you had y squared minus x squared equals -4? Well, you don't want a negative here. I always like to have a 1 there if I can. So I would divide both sides by -4, and I would get minus y squared over 4 plus x squared over 4 equals 1. This is a left-right hyperbola. Yeah. So where the x-intercepts are 2 and -2. Okay. So, and if you plugged in different values for c, you'll get, you know, a collection. So you would get more up-down hyperbolas, and you would get more left-right hyperbolas, and that would be your contour map, a bunch of hyperbolas. Yeah, pretty cool, huh? Level curves. Pretty easy. Not hard to get. So you can extend this concept of level curves to level surfaces. Woo, what do I mean? Well, if you have a function of 3 variables, remember you need 4 dimensions. No way can you graph it. But even though you can't graph it or visualize it, you could still talk about its having level surfaces. So that's kind of interesting. It's like very hypothetical here. So level surface. So if you have a function of 3 variables, can't graph it, you need 4 dimensions. But if you can set that function to a constant, you can talk about level surfaces. So here's a function of 3 variables. Cannot graph it. No way. But if we could graph it, what would its level surfaces look like? So step 1, set the function equal to a constant, any constant, c. So 4x squared plus y squared plus z squared equals a constant. And now we're in 3D. Now this is an implicit function of x and y, and we can graph it. Pick a value of c, your favorite c, like 1, or 5 or whatever. And I claim this is going to be a bunch of ellipsoids. Ellipsoids for different values of c. So you get a whole collection of eggs. Ellipsoids kind of look like eggs. Yeah, I'm not going to graph any of those. I'm just going to leave it at that. Okay. Now, let's just, to wrap this whole section up, this is where I kind of ask you to just sort of imagine other dimensions. We're not going to really get into lots of strange dimensions in this class, but if you're taking a linear algebra class, they do. They don't graph, but they deal with many dimensions. So you can talk about functions of more than even 3 variables. Like, let's say you were trying to model the United States economy. There's all sorts of variables that could get thrown in there. Shoot, that would be a function of like maybe 50 variables. The tax rate, the unemployment rate, all sorts of things would go into that function model. So you could have a function of many variables. Okay, so you just don't graph it. You would just do some work with it. All right. So this summary table, what I like about it is it kind of gives you the flavor for everything. So the notation that you would use for functions of like lots of variables, here they have n variables, x1, x2, x3, all the way up to xn. And then the xn plus 1th variable is what they use to call the whole thing. So, like when you have a function f of x, what do you use to call it? Well, what's the alphabet letter that comes after x? Y. Similarly, when you have f of x, y, z, or excuse me, f of x, y, we'll stick to function of 2 variables. What's the alphabet letter that comes after x and y? Z. So usually you name it like that. Except, what if you have f of x, y, z? There's no alphabet letter that comes after z. You're done. So typically they'll name it something else like w. But anyway, I digress. So here you have a function of 1 variable, and you studied these in calculus 1 and calculus 2. That's the explicit form. But if you put everything on one side and 0 on the other, that's an implicit form of it. And the graph is in 2D. If you have a function of 2 variables, the explicit form is z equals f of xy. If you get everything on one side and 0 on the other, you can write it in what's called implicit form. And by the way, we care about this for later. We're going to do a whole bunch of implicit form stuff. So I'm throwing this out there because I'm planting a seed for later. And you can certainly graph a function of 2 variables. You need R3. Now, if you have more than 2, you get into interesting territory. Here's a function of 3 variables. Here's implicit form. You would graph it in R4, but you can visualize that. I can't. And you can talk about n space and n plus 1 space. Because you would need n plus 1 space if you had a function of n variables. This is a nice summary table, and that's why I love it so much. So we are now officially done with this section. Congratulations.